In this video, I want to talk a little further about the normality assumption for the simple linear regression model. So first, let's remind ourselves what's the simple linear regression model. I have a outcome y, which equals beta naught, which is the intercept, plus beta 1, which is the slope, times xi plus some model error. Okay, so for I equals 1 to n. Right? And the first assumption is that xi's are non-random. All right, so these are fixed numbers. They are non-random, which means that they have to be observed with little or no measurement error. Okay, epsilon i's are IID, normal with mean 0, variance sigma squared. All right, let me break down what is IID. IID, that means that we have independent and identically distributed. All right, so the fact that these guys are independent, that's pointing out that the model errors are uncorrelated. All right, so that's what independent is pointing out, that epsilon i's are uncorrelated. Next, we have the word identically. That's pointing out that for all I, we have this exact same distribution, right? So sigma squared, it doesn't change depending on I. So it's the exact same sigma squared for all i's. That's also called the homogeneous variance assumption. Okay, so now using these two assumptions, there's a lot of results that are directly related to these two assumptions. So first, the expected value of yi. Now, sometimes you'll see this written as the expected value of yi, and sometimes you'll see it as the expected value of yi given xi. Since xi is non-random, you can write it either way. They mean the same thing. All right, so if we take the expected value of our outcome, yi, using properties of expected value, that's basically the expected value of each piece of the sum. And since nothing is random up front, these guys are just themselves, right? Because they're non-random. This is a constant, beta naught. The expected value of beta 1 times xi, those are both constants. They are non-random, so it's just themselves. And then the expected value of our error is 0 because of our normality assumption, in particular because of the mean of that normality assumption. Okay, and similarly, we can figure out the variance of yi. Again, you might see that as written as the variance of yi or the variance of yi given xi. It doesn't matter. Either way, they're the same thing. Unlike the expected value, which you do have xi on both sides of the equation, the variance, you're not going to have it on both sides because xi is non-random. So the variance of xi is just 0. So I'm not going to write given xi. It doesn't matter. Either way, you can write it. But when I take the variance, basically the only thing that's left is the variance of our model error, because the variance of beta naught and the variance of beta 1 times xi, since those are constants, is just 0, and so it zeroes out. So we're left with this equals sigma squared. All right, and then using properties of the normal distribution, if the model error is normally distributed IID with mean 0 and variance sigma squared, then we can conclude, based off of what those two calculations that we just did above, that yi is also normally distributed with mean beta 0 plus beta 1 xi, right, which is the expected value of yi, comma, the variance of the normal distribution is sigma squared. All right, and again, sometimes you'll see this written, instead of it just being yi, you'll see it written as yi given xi. Right, because you have xi here. Obviously, we do need to know what xi is. Either way you see it, they're exactly the same thing because xi is non-random. Okay, so this normality assumption is very important. Okay, so I want to talk a little bit more about it. And in particular, let's talk about it using an example. So suppose I knew that beta naught equals 0 and beta 1 equals 2. Of course, beta naught and beta 1, we never know what they are when all we have is data, right? But let's just assume that we do know them for right this minute. And then also let's assume that sigma squared equals 1. All right, and if these things are known, then I would know that yi follows a normal distribution, and its mean is 0 plus 2 times xi, and its variance is 1 squared. Right? Which is the same thing as saying it's normally distributed with a mean of 2 times xi and a variance of 1. 1 squared is just 1. Okay, so what does this mean? Well, suppose for, say, xi equals 1. All right? Suppose xi equals 1. When xi equals 1, so let me write it like this. Let me say the distribution of yi given xi equals 1. This is normally distributed with a mean of 2 times 1, and a variance of 1, right? So this distribution, it's a normal distribution, and its mean is 2. All right? So this is the distribution of yi given xi is 1. Now, if I were to go out and find observed values, so xi, and then go out and find some observed values of yi, so these are observed. So I were to say find xi is 1, then I would say, okay, well, let me figure out what yi is, depending on this xi being equal to 1. And of course, it's not always going to be 2. It could be 2, but it could also be 3. It could be 1. The point is that when xi is 1, yi is random, right? Yi is random, and it can be it's more likely to be close to 2, and then less likely to be further away from 2, right? This is what the normality assumption is saying. All right? And then, of course, suppose now if I were to observe a different value of xi, so say xi equals 2 now, then this would have a normal distribution of 2 times 2, comma 1, right? And so again, now I have this normal distribution. It's centered on, instead of it being centered on 2, now it's centered on 4, right? Because 2 times 2 is 4. So the mean is 4. So it's very likely that I would observe values close to 4, and then less likely that I observe values in the extremes. So when xi is 2, right, and I'm observing different values of yi, I can observe values. Sure, I could have gotten exactly 4. Could have also gotten 3 or 5, etc., right? These are all likely values close to 4. Now, could I have observed 7 or 10, right? Yeah, it's just very, very unlikely, right? So how would I figure out exactly how likely that is? Well, I could figure out, well, what's the probability that y is, let's say, greater than or equal to 10, right? And I have this normal assumption. And so I could figure out this probability, that the probability using this normality assumption, using the fact that y is coming from a normal distribution with mean 4 and variance 1. Okay, and we could continue doing this for a lot of different values of xi, right, for all the different values of xi. Let me go ahead and draw this using try to do kind of like a 3D drawing. So this is y and this is x. Okay, so let me try to draw this two-dimensionally. All right, so I have, let's say, 1, 2, 3. 1, 2, 3. Okay, and remember, what is my my expected value of yi given xi, right? Or the mean of my distribution is 0 plus 2 times xi, right? Which is basically, it's just 2 times xi. All right, so it goes through the origin, and then it goes up 2 over 1, right? Up 2 over 1. Okay, so this is the plots of the line of the expected value. Okay, so this is this guy. All right, so then around each observed, so here is, let me do it in yellow. That is the expected value. We expect y to equal 2 when x is 1, but of course there's some random variability around it. So there's like a normal distribution, right? And so when we go out and we observe values, they can be anything around y equals 2, right? And it's less likely that they'll be further away from 2, and more likely that we'll observe values close to 2 when x is 1. All right, and similarly, I can draw a normal distribution around where x equals 2. When x is 2, y is expected to be 4, but it could be more than 4 or it could be less than 4. Y observed can be more or less than 4. But what is important here is that the variability of these two distributions, so the spread of these two distributions, or as I continue for lots of different values of x, the spread of these distributions continues to be the same, right? So the variance is always going to be 1 in this situation. And that's really important. The homogeneous variance assumption is super important, and we're going to talk a lot more about it to come. So that's one of the things I want you to take from this video, that these distributions around the different possible observed values of x, we are assuming that they all have the same variability.